Good afternoon, everyone. I think I'm audible and my screen is visible. Okay. So if there is any issue in presentation or something, please tell me immediately so that I can correct it. Okay. Welcome to the second discussion session on natural convection heat transfer and diffusion mass transfer. So in the last class, we have seen about the basics of convection heat transfer. What are the important terms, terminologies? What are the kind of analysis approaches that we have seen? Today, we will be discussing about the mathematical analysis of free convection. So introduction to free convection is completed. Now mathematical analysis of free convection, which is actually planned to be conducted in 3 hours. So today we will be starting with this part. So we will be generally discussing what is the analytical part, like how can we analyze free convection, what are the important analysis methods, and we will have a few problem discussion, and then we will see what are the important terminologies, how can we analyze that, so how can we connect it to some other aspects of heat transfer. So today we'll start with this, and in the coming lectures also we'll be discussing frequently about these aspects. So let us see what are the contents today. So first we will understand what is a boundary layer. An initial understanding has been given in the last session. Then we will see what are the governing equations, which includes the Navier-Stokes equations plus the our basic continuity equations. Then the energy equation. So Navier-Stokes is a very fundamental equation in building the foundation block of fluid mechanics. So today we'll see that. Then how will it be applied to our convection problem that we can see. So the boundary layer in free convection analysis we can see. Then the effect of natural and forced convection analysis, what we should understand in each of them, a brief summary of that. Okay. So concept of boundary layer, which has been discussed in the previous class. So you can see here 2 figures. So how does a boundary layer growth happen or boundary layer formation happens? How does it happen? So this is a case of a forced convection. Suppose some fan is here, so which is supplying velocity u infinity, which is called as a free stream velocity. So when it blows over a plate, the fluid layers which are immediately in contact with the surface comes to rest. So the velocity is 0 here. This is also called as a no slip condition. And while the fluid layers above, they will be having a velocity difference, that gradient. So why is it having a velocity gradient? Because due to the viscous effects. So there will be a velocity gradient existing here, while the outside free stream will have u infinity velocity. So there is a marking of a boundary here. So this is called as a boundary layer. So this is the boundary layer edge. So in a free stream flow like this point is called as the leading edge, from where this boundary layer formation starts, and it ends at the trailing edge. Okay, so there is a free stream. So inside this boundary layer effects are happen. So what you need to understand is, inside this boundary layer, there will be viscous effects, which will be significant. While outside the boundary layer, there won't be much, or there is, we can assume 0 viscous effects in compared to the boundary layer. So all are relative. So in compared to the boundary layer. Okay. So you can see here a quantity. You can see here a quantity called as delta. You can see here a quantity delta. What is this delta? That is called as the boundary layer thickness, which is the thickness of the boundary layer. So what marks this thickness? That is actually the point at which the velocity will be equal to 0.99% or 0.99 of u infinity, 99% of u infinity. So if you join all the lines which are connected by this, so wherever the velocity is actually 0.99% of the free stream velocity, if you connect them, you'll be getting a boundary layer. So up to that edge, these effects are significant. So this has been determined experimentally. So through different aspects, so it is found that, so 99% means which is very close to the free stream velocity. So there is a very sharp edge. Although you should understand that this is magnified in the actual scenario, this boundary line will be very thin. It's very thin. Suppose in an aeroplane where this flight is taking off, there will be boundary layer formation in the wings. So that will be very close. So you should never think that this is so large. It's very delta will be in the range of very less values, maybe in millimeter range or some that ranges. Okay. So similarly, there is thermal boundary layer. Thermal boundary layer. So which is also caused because if a free stream is coming with a temperature T infinity. So when it approaches a plate, so you can see here the temperature is actually forming from this leading edge. So those layers which are in contact with this surface, suppose if this surface is having a TS, so those layers which are in contact with the surface will be getting the temperature of that surface, and the remaining layers will be having a free stream T infinity, and inside there will be a velocity, temperature gradient inside. So that is also created due to the viscous effects. So you should also understand that unlike in velocity boundary layer, this boundary layer growth need not start from here. It can also start from another point, say here, because heating can happen even from here. So in that case, this this length is called as the unheated length. So this can also grow from here. It's need not to be like it. But in a velocity boundary layer, you can see that it will start here because the fluid layers would come to rest. So that is another aspect of this. So you can see here this boundary layer. So you should never indicate an arrow like this because it's not a vector quantity, it's a temperature. So just show that TS. So you can see that there is different gradients here. So T infinity, you can see this TS is greater than T infinity, right? Because the length of the line is actually bigger, TS. So this is a heated plate. If it was a cold plate, then it would be how it would be like it will be lesser and it will be finally increasing to a larger outer value. So this will be T infinity and this will be TS. So there is also a thermal boundary layer, delta T. This is also called as delta H in velocity boundary layer. So the region of the fluid in which this temperature gradient is called as a thermal boundary layer. And this delta T is quantified like this. It is Ts minus T divided by Ts minus T infinity is 0.99. This is the quantification aspect. So here it was U is equal to 0.99 U infinity. But in a heated plate condition, this quantification is like this, Ts minus T. So T is actually a function of Y here, Y, X, Y. By Ts minus T infinity is 0.99. Otherwise, we can write it, rearrange it, Ty equal to Ts minus 0.99 into Ts minus T infinity. Okay. So that quantification is different here. So that is called as a thermal boundary layer. So that is also a very thin layer. So in any kind of analysis, so there is actually, we will divide it into velocity boundary layer and thermal boundary layer. So that will tell us how much, what is the velocity distribution as well as temperature distribution inside these layers. So another aspect you should look at is, suppose U infinity is the free stream is flowing, the temperature is also taken along with the free stream velocity. So there is a thermal boundary layer as well as a velocity gradient here. So here U is 0 and here U is equal to 0.99 U infinity in the free boundary. Outside it is U infinity. Okay. So you can see delta T here, delta T of X that is actually created. So what we have to understand is, so this is called as a boundary condition. So at the boundary where the plate is placed, so if the plate is heated, which means there is a heat flux QS applied. So the fluid layer will be like this. So at the boundary, which is actually this edge, we can write the boundary condition to be QS is equal to minus KF into dou T by dou Y at Y equal to 0. There's a minus missing here, which means that it is temperature gradient is flowing from a higher temperature to lower temperature. So if you take Y equal to 0 is this point. So dt by dy at Y equal to 0. If there is a temperature profile, this dt by dy at this point gives the temperature gradient at the base plate. So whatever heat flux is applied, you can write like this. So you have to note that this is K of the fluid layer. So fluid is also having a thermal conductivity. So that heat condition should be actually balanced with the convection condition. So at the surface, we know that there is no fluid motion because it is at rest. And this energy transfer happens by conduction. And relating it to Newton's law of cooling, which states that HA delta T, we can equate that to this factor. So Kf into dou T by dou Y, there's a minus at Y equal to 0. So A is not there because it is flux. So H delta T is equal to minus Kf into dou T by dou Y at Y equal to 0. So H is also, we can write it as minus Kf into dou T by dou Y, the whole divided by delta T, which is Ts minus T infinity. So we will be getting the convection coefficient H from this relation. So in experiments and all, we can quantify the H value like this, determining the temperatures and the temperature gradient inside this. So if we dip a thermocouple inside this, inside this boundary layer, suppose you can get the temperature variation inside this profile. Okay, so in experiments, we will be determining it like that. So another aspect which was discussed, so this was actually discussed roughly in the previous session, this boundary layer approximation. So we know that suppose a plate or something is heated, boundary layer will be obviously formed. So when that is happening, there is a flow happening. So there is a U infinity and T infinity in this direction. So which is that direction? That is X direction. Also there is a Y direction. So the velocity in the X direction is denoted by U and the velocity in the Y direction is denoted by V. Okay. So you can see here, so there is a heated surface also. So U is a function of Y and T is a function of Y here. So fluid is flowing like that. So you can see a velocity distribution profile and or the shape of the velocity distribution profile, temperature distribution profile. Okay. So we will make some assumptions in this analysis because it will make our calculations or any kind of further simplifications very easy. So one assumptions or one reasonable assumptions you can always make is when a boundary layer is formed and the flow is happening in this direction, we can assume V component to be very much less than U. Suppose U is maybe suppose you say 10 meter per second. V will be in the range of 0.05 meter per second, suppose. So because there is not much flow happening in this direction. So the boundary layer growth is actually proceeding in this direction. Then the velocity gradients. So obviously V is very less. So the velocity gradient will be dou V by dou X, which is equal to dou V by dou Y will be equal to approximately 0. So if you look at if X quantity dividing by another quantity, so it is also called as a scaling analysis. Suppose if it is 0.05 V and X value is very large, the plate is very large, say 10 meters or something, it is actually going to 0, right? 0.0005. So we can neglect that also. Then another assumption which is made is dou U by dou X is very much less than dou U by dou Y. So we know that U is existing, say 10 meter per second. So dou U by dou X. So dou U by dou X is very much less than dou U by dou Y. What is the basis of this assumption? Because if X is very large, so Y is actually up to this boundary layer thickness only. So suppose if it is 10 and the plate length is 10, then dou U by dou X suppose it will be approximately equal to 1. And suppose the Y it is actually the thickness, maybe 0.1 meter or something, then or 0.1 meter. Then 10 by 0.01 will be how much? 10 into 100, so 1000, which is actually very greater than dou U by dou X. So this assumption is also taken into consideration. Similarly, in temperature gradients, we assume dou T by dou X very much less than dou T by dou Y. Similarly, X is under the assumption that X is very large, greater than Y. So there's a steady gradient developed in this direction. So that assumption also we can consider. Okay. Now let us look at the free convection boundary layer. So the free convection, also called as our natural convection, because it is available at free, no energy, because we are supplying not energy. The flow is happening by virtue of the density or the kind of the temperature variation happening in the fluid. So you can see there is a plate here. So maybe it can be a heated plate, and the outside fluid, which is our ambient condition, suppose our ambient conditions. So it is having a temperature T infinity and density rho infinity. So there is a gravity acting in the negative y direction. Because if you assume y and x to be this, so you please note that in all these assumptions, you have to clearly notify what are the directions of x and y. So x is actually taken here to be in the vertical and y to be here in the further discussion. Please note that. So any velocity in that direction will be u, and any velocity in this direction will be v. So as soon as it's heated, so the layers which are closer to this heated plate would gradually rise from here and it will get convected. So you can see the velocity profile like this. So, and the outside fluid is at temperature T infinity and U infinity, rho infinity. So all the ambient conditions will be denoted by infinity. So T infinity is the outside. So this marks the velocity boundary layer thickness. Okay, similarly, this marks the thermal boundary layer thickness. So it is a heated plate, so Ts is definitely greater than T infinity as noted here. So the outside temperature is here, T infinity. So it is called as quiescent fluid, or we can also note it as stationary fluid because it is not in motion. Only these layers are in motion. Outside it is 0, no U component, no V component. Okay, so that is happening. So in the further discussion, what we can see what will happen if the plate is cooled. We just think about that. What will happen to the boundary layer if this plate is cooled? Okay, so what will happen? Maybe you are keeping a Pepsi can or something. What is the, suppose it's a Pepsi can. if it is a cold Pepsi can, how will the boundary layer form around the surface? Okay, if it's a hot plate, then like in last class we discussed a problem of iron box. So there the plate was hot. So there the boundary layer formation will happen like this. So just think about that. So that is our analysis. Okay. So now we need to analyze this mathematically, how this U, T and all are quantified. So for that, let us have a quick understanding of this governing equations of fluid flow. So the essential governing equations of fluid flow is this continuity equation. So all these detailed derivations are all available in fluid mechanics heat transfer by Sengel and Simbala. You can refer that. You will get a complete derivation of these equations. So in the continuity equation, so we can see this is the density and rho is the density and V is the velocity component. So whenever a fluid is flowing in a 3D space or something, suppose this is a fluid element, it will have three components. So it is 3x, y, z. In cylindrical coordinates, it would be r, theta, phi. Suppose in Cartesian, just fluid element, it will have three velocity components. One is u, which is in the x direction. Then v, which is in the v, which is in the y direction, and w, which is in the z direction. So let us expand this. So this dou rho by dou t, this is called as a divergence operator. So we can write rho v is actually a vector. So we can use this vector operation. So this will be when expanded. So del operator, it is dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. And v vector would be ui vj wk. We can notate it like that. Ijk are the unit vectors in the xyz directions. So expanding that, it would come dou rho by dou t plus dou of rho u by dou x. You can just verify this operation, just taking the dot product, plus dou into rho v by dou y plus dou into rho w by dou z equal to 0. So if it is a steady flow, as I discussed in the previous session, steady flow means the function is not a property is not a function of time. So density won't vary with time. So if it is steady flow, we can neglect the t term. And if it is an incompressible flow, density is not a function of x, y, z. Obviously, previously it was not a function of t. So we can add. So we can take the density term outside. So it will come dou u by dou x plus dou v by dou y. And if it is a 2D flow, there is no planar flow, then there is no 3D, z-axis component. So we can neglect this also. Okay. So it simply reduces to dou u by dou x plus dou v by dou y equal to 0. This is a 2D incompressible steady flow. So if you know the u and v components, you can check whether if the flow is continuous by substituting in this equation. So that's the basic understanding. Okay. Then comes the conservation of momentum equation or Navier-Stokes equation. So the detailed derivation is also available in the literature. You can just refer. So I will quickly mention all the terms inside this. So this is called as the our density, and this is our called as a local term, which is actually time term. Then this is called as a convective term. So this operator I will explain how that is expanded. Then this is the pressure gradient term. And this is the body force or the weight here. And this is also a vector. Okay. And this is the viscous term. So the conservation momentum equation or Navier-Stokes equation is actually, the net force acting on a system is equal to rate of change of momentum of the system. So delta F value is actually expressed in the Navier-Stokes equation generally. So when a fluid is flowing, you know that there will be a pressure gradient that is driving the flow. Then there will be weight of the fluid element. Then there will be viscous forces within the fluid element. So these are the general forces that is acting in the flow condition. So if any other force is there, that components would add up in this term. So this is the basic building block of equation of fluid mechanics. So you can, if interested, you have to refer this derivation. The detailed derivations are present inside that. So this term, convective term, I will explain, that is actually denoted by this. Suppose here also momentum can happen in X, Y, Z. So momentum is conserved in X, Y, and Z direction. Suppose we are expanding this in X direction. Then comes rho dou U by dou T plus this term is actually, you have to expand it like this, U dou U by dou X plus V dou U by dou Y. Why I'm taking U? Because it is in X direction. Plus W dou U by dou Z is equal to minus dP by dx or dou P by dou X in the X direction plus rho G X. Suppose if fluid is flowing, so rho G X, the gravity in the X direction. So it's a vertical, anyways, gravity acts in the downward direction only. So that term we can neglect in X component if X is taken horizontally. Then mu into del square U, which actually takes into dou square U by dou X square. Similarly, you can write in Y direction also, Z direction also. There these components would change to V and W respectively. Okay, so in a steady flow condition, we can neglect this. So that goes to zero. Only these components are present. And if it is a 2D case, then we can neglect this also. So all our analysis are of 2D type. So we need only these terms. Then there is a pressure gradient term and the body force term and the viscous term. So that you can refer to all these aspects. Okay. Next comes the energy equation or the conservation of energy equation. It's actually an expanded form of maybe if a fluid element is here, whatever energy comes in must be equal to energy out. And if there is a energy generated inside, energy out equal to minus energy in equal to energy generated inside, rate of energy. So this is actually an expanded term taking into consideration all these aspects. So here also temperature, velocity is not the case. So energy, temperature is the case. So dou T by dou T, rho is our density, Cp is specific heat. Then comes the convective terms. U is associated with the temperature. You can see velocity components are associated with the temperature. Then this part is called as a diffusive term. Then this part is actually called as the viscous dissipation term. So there will be viscous forces inside. So that will be actually adding up to heating of the fluid element. In most of our discussion, we will neglect this part. because viscous dissipation we will assume it to be negligible. And if we rewrite this, we can just take, if it is a steady flow, we can still write rho Cp into U dou T by dou X plus V dou T by dou Y equal to K del square T. So then rho Cp can be taken to other side. So K by rho Cp is actually alpha, which is a diffusivity, thermal diffusivity. So that factor you can determine. If you know the K rho Cp of a particular fluid, we can determine this. So del square T, how will you explain? Del square T is actually dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square. Okay. Hope that it is clear. So in case you have any doubt, you can ask me, or the detailed derivations, it's already there in the textbook. You can refer to heat transfer, any of the textbook. In Cropper also, it's available. Okay, so let us see how that is going to be useful in our analysis. So in the natural convection situation, like I was saying, that momentum conservation, as I have told previously. So what we have done is actually this, we will be taking this convective part steady state situation. So what is happening? So rho is here, but we have actually brought it to the other side. So that's why the rho is here. And rho gx other terms are divided. Here it is nu. Nu is actually ratio of uh, dynamic viscosity to density. So this is called as our kinematic viscosity. Okay, we have just modified that Navier-Stokes equation in this manner. Okay, so when we write that, we will be getting this u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x minus. So please note that x is in this direction. So x is in this direction, y is in this direction. Okay. So minus 1 by rho dou p infinity by dou x minus gx plus nu dou square u by dou y square. Okay. So here one of this u, v and everything is known. Suppose if you know, but one determining factor is this pressure gradient. In force convection or in a flow through pipe, we know that this pressure gradient is actually pressure gradient. How is it actually determined? Dou p by dou x, we know, because suppose a pump is pulling a fluid through a pipe. So we know what is dp by dx. There is a pressure driving that thing. But in natural convection, we are not supplying any kind of pressure gradient or something. So how that is then determined? So you see here, I have added dou p infinity by dou x is equal to rho infinity into g. So from where does this equation come? So what you should understand from this. So it is a density of the ambient is actually driving this. So density of the fluid domain or the area in which we are considering is continuously changing. Why is it changing? Because it is getting affected by the temperature. So what all fluid layers which are in contact with this surface, that will be affecting the density of the surrounding fluid. So that's why, you know, like when you open a teacup in air, it will get cooled down. Like it will be releasing heat and getting cooled down. So what is happening? So the tea is inside. So it's a hot tea. Outside there is a T infinity, or it is at a lesser temperature. So the hot layers, which are the fluid hot layers, which will be less denser, and it will rise to the top and it will get cooled down, releasing heat to the surroundings, and it will settle down, getting denser. So this is actually forming a current inside. So it's a gradual process of cooling down. So it is actually happening because of the surrounding fluid layers outside. So density of the fluid is actually getting affected by temperature. So from where do we get this thing? So So if you analyze, this is X momentum equation, right? I have told before, we also have Y momentum conservation equation. So if it in the Y momentum, what all changes will happen? I'll just write over this. V, is it V? No, it is U dou V by dou X plus V dou V by dou Y is equal to minus dou Y by dou P infinity by dou Y gy, then that will change to dou V by dou Y square. So previously in the boundary layer approximation, I have told that suppose this is a horizontal plate. In that case, I have told if it is U and this is V, we can neglect this V. Suppose I have told that value maybe 0.05 or this is larger value 10. But here it is a vertical plate. So just see. So this is our X direction. This is our Y direction. Okay. So here just have a look. So here our U is in this direction and V is in this direction. So here the flow is happening in the vertical direction. Okay. So here which part we can neglect? V part. So that we can assume to be zero, not zero. It is very much less than U. So U is very larger than V. So we are neglecting this part. We are neglecting this part because that is actually derivative is zero. Then this also goes to zero. And what about Gy? Gy is in this direction, isn't it? So what has happened? Dou P infinity by dou X as going to be zero. Dou P infinity by dou Y is going to be zero. So what does that mean? P, it's actually not P infinity, it is P actually. So because it's not surrounding, it's a pressure gradient driving the flow. So dP is, P is a constant with respect to Y. So P can be only function of X. Suppose if P is a function of X, then definitely dP by dy will be zero, right? So what is happening is the density is actually varying in the X direction and we are substituting it back here. So dP infinity by dx is equal to rho infinity into G. So that we have to apply at every point of this direction. So delta P is rho minus rho infinity. So substituting that back here, U dou U by dou X plus V dou U by dou Y plus G into delta P by rho. Delta P is actually rho minus rho infinity. Just only a substituting because now dP is by dx is gone. I'll just erase this. So that is actually gone. So so just resubstitute all these values. So gx, so here also it is actually gx because x is, you should think that it is in this direction. Because I am using this convention because in most textbooks it is x and y like this. So while studying, you shouldn't get a confusion. That's why I'm using. It's convenient to use y, but it's better that you learn with this. So substituting it back, you will be getting. Okay. But now another challenge comes. How will you determine delta rho? Okay. So one question we can ask here is this compressible flow or an incompressible flow? So in order to satisfy the continuity equation, dou u by dou x plus dou v by dou y equal to 0. So in that we have taken density to be constant and eliminated. So that is actually satisfied. So here in natural convection, you should understand that all the density is assumed to be constant except in the buoyancy term. So this is called as a buoyancy term. Okay. So this is actually contributing to our buoyancy term. This is our buoyancy term that I will explain. So in continuity equation, we treat it as constant density, but here we will assume that it is varying with respect to, because here the driving force is density variation. How that is created? That is due to function of temperature. So what a scientist named as Bosnus said is, he just gave a term beta. This is called as thermal expansion coefficient. He defined a term. So it's according to that. So it is actually defined like this: minus 1 by rho dou rho by dou t at constant pressure. It is called as a volumetric thermal expansion coefficient. So according to him, if it in the case of a fluids, we can determine a coefficient like this. So which will be characteristic for a particular fluid. This has been determined through several experiments. So where density is connected with temperature using a constant. So that will be remaining a constant for a particular fluid. Okay. So what he said that for very small temperature variations, suppose inside this boundary layer there is T and T infinity. If that T minus T infinity that is not too high, then we can assume that we can relate that with density as a function of linear function of temperature. So what if you expand this, you can see beta is equal to minus 1 by rho dou rho by dou t at constant pressure. So which means that at constant pressure, rho by t is a constant. Okay. So I hope that is clear. If you have any doubt, you can ask me in between. Okay. So 1 by rho into, we can also write it as delta rho by delta t at constant pressure. So delta rho is simply rho infinity minus rho. So in a fluid layer, if this is rho and this is rho infinity, so it is, so here it will be t and it will be t infinity. So you can see that variation. So it is actually a constant value at a particular temperature. So if it is for an ideal gas or something, suppose if we treat it as an ideal gas, like if we treat air to be an ideal gas, we know the ideal gas equation. P is equal to, PV is equal to MRT, or P is equal to rho RT, that relation. Yeah, P is equal to rho RT. So otherwise we can also write P by rho T is also P by RT equal to rho. So just substitute. So we have rho equal to P by RT. Just differentiate that with respect to temperature. We will get at constant pressure. So pressure is constant here. RA anyway is constant. It's a universal gas constant. So just differentiate that. So we will be getting, what will we get? P by R into minus 1 by T square. Derivative of 1 by T is minus 1 by T square. So that relation, simply we can substitute it here. So when we substitute, what is happening? Beta equal to minus 1 by rho into minus P by RT square. This is, but what is P by RT? P by RT is again rho. So we can also write minus 1 by rho into rho by T. So that simply reduces to 1 by T, where T is in Kelvin. Okay, so for determining the volumetric thermal expansion coefficient, you just need to determine the temperature in Kelvin of that fluid. If that fluid is having a variation from T to T infinity, what we will do in calculation? We will determine the bulk fluid temperature, which is actually T, assume if it is Ts, T infinity by 2, we will take an average value of that to determine this beta. From that, we will determine beta equal to 1 by TBF. So that will be used in all our calculation. So beta is equal to 1 by Tm. It is also denoted as bulk mean fluid temperature. So we will get that. It is actually 1 plus Ts plus T fluid, surrounding fluid temperature by 2. So temperature has to be in Kelvin. So that you need to note. Okay. So from the previous relation in that equation, we know that beta equal to rho infinity by rho divided by T infinity minus T into 1 by rho. So substituting it back, we can see rho infinity minus rho equal to rho beta into T infinity minus T. See, now density is actually removed and we are inserting temperature into the x momentum equation. See, we have replaced that. Now we have velocity and temperature only. So by Bose-Einstein approximation, we have eliminated density. We have eliminated, replaced density with temperature. So beta is here, which is the volumetric thermal expansion coefficient. So this is the x momentum equation. X is actually always known that x is in the vertical direction. Okay. So in short, we can write the governing equations of natural convections like this. The continuity equation, dou u by dou x plus dou v by dou y equal to 0. And the momentum conservation equation, which is in the predominantly in the x direction. X direction is our vertical direction. So u dou u by dou x plus v dou y is equal to g beta into t minus t infinity into nu is our kinematic viscosity. Don't mistake it with this velocity. It is a kinematic viscosity. Just got unit of meter square per second. So this is this. So these are our convective terms. This is our buoyancy term, which is actually driving this flow. This is a driving force. And this is our viscous force terms, viscosity of the fluid layers. And similarly, energy conservation equation, as I said, so this is actually not U, it is actually T. Okay, so currently we can write it like that. So energy equation, just substitute that values and you'll be getting the energy equations also. So these are the three governing equations of natural convection flow. So here we can make this substitution, please understand, because it is a natural convection. Because it is a density driven flow or buoyant force driven flow. That's why temperature term is coming. So one another aspect you have to note here is that here the temperature and velocities are coupled. So you have to understand that temperatures and the velocities are coupled. So solving them is not an easy task in many situations. If you get a temperature profile directly, you can directly substitute inside this and you can easily solve for you. Suppose you get a temperature profile, something in a linear fashion, say AB plus AT S plus some TY or something relation. Just substitute that here. So then you will be getting definitely the U function, U as a function of temperature. So they are actually coupled each other. So in velocity term, temperature will be existing and temperature term, like it is also like connected with this convective terms. So solving some situations, we will make some approximations and boundary layer theories so that we can easily solve them. Okay. So next we can see just an understanding of non-dimensionalizing of equations. So this is very useful. Just have a basic understanding. It will be very useful to you. So what is non-dimensionalizing is that you will be converting these components into non-dimensional factors. Okay. So what we have done is we will substitute that x terms in terms of non-dimensional. So together we are making the equation non-dimensionalizing. But the question is, why should we non-dimensionalize? So why are we non-dimensionalizing? Because it is independent, becoming independent of the length scales. So we can apply conveniently to any system irrespective of its length scales. We are only interested in the non-dimensional numbers. So if two systems, system A and system B, suppose they are having similar non-dimensional numbers characterizing this. Suppose if it is non-dimensional number is called as some D. And here also it is characterized by non-dimensional numbers D. Then they will exhibit similar kind of behavior in natural convection or in any system. So it is irrespective of the size or the dimensions. So it's a scaling analysis. So we can predict in each of them. Suppose if something is happening in the system, we can predict that in another system having same non-dimensional parameters, it will be exhibiting a similar kind of behavior. So we will discuss some problems in upcoming sessions, how that can be done, how that will be useful. Okay, so here we have non-dimensionalized that. So U star is actually substituted with U by U ref, and V star is substituted by V by V ref. U ref, its U reference is called as the reference velocity. Okay. Okay. Then our G beta, that buoyancy term, is also divided by this factor. And this is the non-dimensional RE number or the Reynolds number. So we will see that why it is. So here I have introduced U ref factor. So why is it like that? So U reference is also called as reference velocity. Why we need that in natural convection? Because in forced convection, we know that there will be U infinity, which is imparted by some kind of a velocity. But in natural convection, there is no reference velocity. So we need some reference velocity to compare with that. So we are trying to non-dimensionalize this equation. Suppose we know Reynolds number, we keep it as VL by nu, which is having no dimension. So we are keeping a reference velocity like this. So T star is anyway non-dimensionalized because it is having no unit. This is also having no unit, no unit, no unit. So just we can see that if this term has to be non-dimensionalized, then the denominator must be having the same dimension of the numerator. So U reference square must be equal to G beta into Ts minus T infinity into L, or U reference equal to root of G beta into Ts minus T infinity into L. Okay, so that is the reference velocity we can assume. So now this part comes the Reynolds number. So here we need to determine this RL. So we have eliminated the kinematic viscosity. It is actually included in that. So in Reynolds number term, as I wrote here, it is VL by nu. But here we don't have any V. We will just use U reference into L by nu. So U reference we have previously seen root G beta into Ts minus T infinity into L by nu. So take this L term inside the root and the nu term inside this. So that will become G beta into Ts minus T infinity into L square by L cube by nu square. Okay. So that is a REL term. So if we take the square of that, we are getting another dimensionless number. What is that? So that is our Grashof number. G beta into Ts minus T infinity into L cube by nu square. This is our Grashof number, which is equivalent to our Reynolds number in forced convection. So Grashof number is that dimensionless parameter that we will be getting from here. Now energy equations also we can non-dimensionalize. So similarly, we will define like this. So here Prandtl number also comes to make it non-dimensionalized, so that you can refer that is available in the textbook itself. So now let us look at natural and forced convection. So When forced and free convections are present, that the situation is slightly different. So first, I have told you Grashof number is characterizing natural convection, and Reynolds number is characterizing our forced convection. So Richardson number is an important number, which is actually signifying which of them is more significant. So Richardson number says that it is a ratio of Grashof number to Reynolds number square. So if Grashof number to Reynolds number square is greater than 1, what does that mean? Which means that this is the term representing natural convection. This is a forced convection. So if that means, what does that mean? So natural convection is more. If it is less, means forced convection is more. This means natural convection is equal to forced convection. So if in a particular system characterizing this number, we can conveniently say which of them is predominant and we can neglect the other part. Also, please note that forced convection is Nusselt number is a function of Reynolds and Prandtl number, and in free convection, it is a function of Grashof number and Prandtl number. So when we are getting correlations like this, we can just simply write C of Reynolds number raised to m into Prandtl number raised to n. So Nusselt number, which is actually characterizing our heat transfer. So in natural convection, we can write, we don't write actually Grashof number, we can also write, but mostly it is characterized by Rayleigh number. Okay, so see, Rayleigh number is an important number. So that is also just simply our Ts minus T infinity into L by nu alpha, which is actually our product of Grashof and Prandtl number. Okay, so just understand these factors for forced conversion. Nusselt number is a function of Reynolds and Prandtl number. Because what is the importance of Nusselt number? From Nusselt number, we can determine the heat transfer coefficient in the heat transfer. So in free convection, Grashof number and Prandtl number will be effective. So correlations for natural convection, there are several correlations. With respect to geometry, it may vary. See, so Rayleigh number is an, as I told, is an important parameter. It signifies whether the flow is laminar or turbulent, like the Reynolds number. So if it is less than 10 raised to 9, it is laminar. It is greater than 10 raised to 9, it is turbulent. So in between also, they are suggesting some correlations. So you can see here several correlations. So for inclined plate, what should be done? Then horizontal plate, what are different conditions? Vertical cylinder. See here, a vertical cylinder can be treated as a vertical plate, satisfying this condition. So we can also treat like in some situations like this. So it will make our calculations more easier. And horizontal cylinder is there, then sphere is there. So for that, there is a correlation. So all these are available in heat and mass transfer data book. Just get our temperature conditions, obtain K, rho, mu, Cp, every values, obtain the correlation, determine the Rayleigh number, Grashof number, etc. And that will make our calculations more easy. Okay. So we'll discuss one problem. So two problems. I don't know if we'll get time. We'll discuss both. Two problems are there. I think we'll get time. So we just see it immediately. So from the basic understanding only, like we will see some problems. So you can see here an electrical heater in the form of a horizontal disc of 400 mm diameter. So there is a heater plate. So just I'll draw a schematic one diagram. So this is a disc. There is a disc at the bottom. So it's a plate. So that is actually electrically heated by heating, and there is an oil inside. So we will be supplying electricity through this. It will heat it. So that will transfer heat into this. And the dia is 400 mm. And the oil temperature is 5 degrees Celsius. And the surface temperature of the base plate is 70 degrees Celsius. So question is, calculate the power required. How much power we need to supply electrically so that this will start heating. So there will be, when it is heated, how much power we should supply. So oil at temperature of 5 degrees Celsius. So surface temperature, it will be remaining same at 70 degrees Celsius. So how much power should be supplied? So in this thing, we will assume that oil is quiescent. Quiescent means it is almost stationary and in quasi-steady state. So that I will explain quasi-steady state, which means that we will see what is quasi-steady state, which actually just means that T infinity is constant, which means fluid temperature don't change with time. But that is not the case, we know. But assuming that condition, how will we solve? Okay. So first we need to determine the engine oil properties, because convection, our working fluid is not air, our working fluid is engine oil. So that is undergoing convection process. It's a fluid, so it is undergoing the convection process. So the bulk fluid temperature first we will determine. So the fluid is at 5 degrees Celsius, so which is our T infinity, and the heated plate, which is at 70 degree Celsius. So we will convert that into Kelvin. So finally 273 plus 5 plus 273 plus 70 by 2. So that will come to be 310 Kelvin. And from that 310 Kelvin for engine oil from heat and mass transfer data book, you can get the values. Nu, which is a kinematic viscosity, 288 into 10 raised to minus 6 meter square per second. K, which is equal to 0.145 watt per meter Kelvin. Then alpha value, which is our thermal diffusivity. So that is 0.847 into 10 raised to minus 7. And also the beta value, as I discussed, just use this equation 1 by TF. So 1 by 310 Kelvin. It has to be in Kelvin. So that will come to be 0.7 into 10 raised to minus 3. So we have all those values. Okay. And here in this equation, we know that we need to first calculate the Rayleigh number for estimating the correlation. So Rayleigh number is G beta Ts minus T infinity into L by nu alpha. So just substitute these values. Substituting these values. So what is the L here? That is a question. So this is not a vertical plate. This is a disk. So L is just characteristic length, which is actually area by perimeter, or which becomes d by 4, pi d square by 4 by 2 pi d. So it is pi d square by 4 by pi d. So that will be d by 4. So just substitute that values, you will get Rayleigh number to be 1.828 into 10 raised to 4 into 10 raised to 7. Okay. So this LC value will be 0.1 meter. So substitute all the values. Ts we know, T infinity we know, beta G is 9.81. So that we are getting the value of Rayleigh number. Now we can calculate the average Nusselt number, which is equal to H bar L by K. But Nusselt number correlation, what will we use? So for a disk, we can see that correlation you can obtain from HMT book, 0.15 into RAL raised to 1 by 3. So substitute that values 0.15 into 1.828 into 10 raised to 7 raised to 1 by 3. So that value would come to be 39.5. So does it have any unit? No, because Nusselt number is a dimensionless number. So H bar equal to 39.5 into K by L. So that H bar will be coming to be 57.3 watt per meter square Kelvin. Okay. Then the heat to be supplied. So how much heat has to be supplied? Heat to be supplied is Q, which is equal to HA into delta T. So HA delta T is H is 57.3 into pi by 4 into D square into temperature difference. So that will come to be 468 watts. So we need to supply a electrical power of 468 watts to keep the engine oil inside this at 5 degrees Celsius, and the brace plate temperature to be at how much? 70 degrees Celsius. So what did we do? What are the steps that we taken? So steps that we have taken is how much? So first we will be calculating the bulk fluid temperature. From that we will be calculating the beta as well as the properties. From the properties, and we will be using the and first we need to calculate the Rayleigh number. Okay, so to see which laminar, turbulent, which correlations to use. So from the properties and estimated, we will be going to the Nusselt number correlation. From Nusselt number correlation, we determine the H bar. From H bar, we use the heat HA delta T equation and determine the heat amount supply. Okay, so I hope that is clear. So next question, one last question. You can stop in maybe in 5 to 10 minutes. So just have a look at the question. It's a good question. So there is an incandescent light bulb. So it is an inexpensive that converts electrical energy into light. It converts about 10% of the electrical energy into light, while the remaining 90% into heat. So what is the efficiency of the bulb? It is 0.9. And the glass of the lamp heats up very quickly as a result of absorbing and to the surroundings by convection as well as radiation. So it says that heat transfer mostly occur by convection and as well as radiation. So assuming that 10% of the energy passes through the glass bulb as light with negligible absorption and rest of the energy is absorbed by natural convection and radiation, determine the equilibrium temperature of the glass bulb. So we need to determine the temperature of the glass bulb. So it is saying that 60-watt bulb in a room at 25 degrees Celsius, and the light which is emitting so that is actually 10% of the energy, which is 60 watt. Out of that 6 watt, 10% passes through as light with negligible, and rest of the energy is absorbed. So let us see how that is actually solved here. So we will assume that there is a steady state condition and air to be an ideal gas with constant properties. The local atmospheric pressure to be 1 bar, because in HMT data book, all the values are at 1 bar conditions. And also we will approximate the light bulb to be of a spherical shape, 8 centimeter spherical shape. Okay. But the one challenge in the problem is surface temperature is not known, because we need to determine the bulk fluid temperature, TF plus T infinity by 2, TS plus T infinity by 2. Only then we can determine this 1 by TF and every value. So what should we do? So what we can do is we can assume a value through trial and error approach. So this is actually a method which mostly used. What will you do is we'll assume a value, arrive at a value, then update that. So we'll assume TS, evaluate the properties, then find the Nusselt number from the correlation, then determine the surface temperature, then update the value and repeat until assumed value reaches the energy balance value. Okay, let us see how that is done. So we will assume a 170 degrees Celsius. Just assume that 170 degrees Celsius. So what is the bulk fluid temperature? So that will be 170 plus what is the ambient temperature? 25 by 2. So that will be 97.5 degrees Celsius, which has to be converted in Kelvin. So beta value will be 1 by TF. So 1 by 273 plus 97.5. So that value will be 0.002699. So what is the unit of that? It is per Kelvin. Okay. Don't forget that. Then with this TF value from the HMT data book, we can determine the K value. K is 0.03077. So what is the HMT air properties? Okay. At this TFL, nu will be 2.279 into 10 raised to minus 5 meter square per second is watt per meter Kelvin. Prandtl number is also 0.7116. So just note the Prandtl number of air. This is only in this range, less than 1. And the characteristic length is actually, it's a spherical shape. So what is the characteristic length of a sphere? Characteristic length of a sphere is A by P. So that will be simply D. In case of a cylinder or a disk, we will take that is to be D by 4 because it is pi D square by pi D. So that will go to D. So that will be 0.08 meter. Okay, now we can determine the Rayleigh number. G beta Ts minus T infinity into D cube, this value, by nu square into Prandtl number, or this is actually nu alpha. So that value comes to be 2.694 into 10 raised to 6. So we have determined the Rayleigh number. So I hope in the previous relation, you know that in a sphere, we can use this correlation. So we are approximating that and using the correlation. Nusselt number is equal to 2 plus 0.589 Rayleigh number raised to 1 by 4 divided by 1 plus 0.469 by Prandtl number raised to 9 by 16, the whole raised to 4 by 9. So if you substitute that value, that will come to be 20.42 watt per meter square. No, Nusselt number doesn't have any unit. So we thought it is H. Okay. From that, we can determine the H value. H value is K into Nu by D. Please note the characteristic dimension is D here. So that value comes to be 7.854 watt per meter square degree Celsius. Okay. And so we have determined the H value and everything. Now AS, which is actually pi d square, which is the surface area of the sphere, which is 4 pi r square, same pi d square, which comes to be 0.2011 meter square. Now it is told in the question that Q is actually going by convection plus Q radiation. So you can see, so what is happening? Q. So it is mentioned that efficiency of the bulb is 0.9 and 60%, 60 watt bulb. So it has to be balanced by Q convection plus Q radiation in a steady state. Whatever heat comes in, so if it is remaining at a particular temperature, it has to go by Q, is conducting by Q convection plus Q radiation. So which is H into A into Ts minus T infinity plus sigma As into Stefan-Boltzmann law. So radiation heat transfer is quantified like that. So when we substitute that value, 7.854 into 0.0, which is the surface area, into Ts minus T infinity. So Ts we don't know, Ts minus 25, because we have assumed a Ts value. Now we are going to determine the Ts value from the equation. So let us see what is that value. So emissivity value we know 0.9 into area 0.2011 into 5.67 into 10 raised to minus 8 into Ts, still we don't know Ts, 273 plus raised to 4 minus 25 plus 273 raised to 4. So unknown value is TS. So we can solve it again by linearly, it's a non-linear equation in TS. So we can just get TS by trial and error approach. Just substitute some random values and see how much are we getting the right side value or how much is there. So from that we are getting TS by trial and error approach. We are getting 169.4 degrees Celsius. So, but my assumed value was how much? I assumed a TS of 170 degrees Celsius, isn't it, initially? So, which is actually much close to this. So, if I haven't assumed 170, then what would happen? Suppose I would have assumed 80 degrees Celsius. Then by this calculation, I would have got something of 100 degrees Celsius, maybe 100 or 120. So instead of that, I assumed like that. So what should I do then? So assumed an 80 and I got this value 120. So what should I do then? So what we will do is we will start again the calculation with 120 degrees Celsius. So it is like an iterative procedure. I will just show. So assumed an 80 degrees Celsius, I got by calculation or energy balance, I got 120 degrees Celsius. Now this is T assumed and this is T calculated. Now what I will do is I will use that 120 degrees Celsius to evaluate all the properties. Then through calculation, I will be getting again how much, maybe 100 degrees Celsius. Then again, I will do the same, 100 degrees Celsius. Then evaluate all the properties. Then I will get something, maybe 160 degrees Celsius. Then again, I will do this, 160. Evaluate all the properties. Again, got it, 168. Then again, I substitute, say 168. Then again, I got 170. Then when I substitute it back again, I'm getting 170 again. So see here the solution has converged. So this is an iterative procedure. So the easiness of your solution starts with good guess. So if I started with an 80, I would have got 170, but I already know the answer. So I calculated that. So I started that's why with 170 degrees Celsius. So when two successive values are similar, you can take that value. So in such property determination, that's one challenge. When surface temperature is not known, you have to assume a TS, get the properties, calculate, and see how much is the difference, TS. So I hope that is clear with everyone. So that was a problem. In the next session, we will discuss more on this convection. We'll be continuously going through the equations, governing equations, and this situations of inclined and horizontal plates. Just a brief summary of that and correlations. Then boundary layer development on some special surfaces. Then some problems on the discussions, and you can see. So 2 more hours are pending on this, and we can see all these aspects and discuss more problems after that. So thank you. If you have any questions, you can ask. So if there are no questions, you can, if you feel like asking at any point of time, you can just mail me or just message me so I can clear that at the earliest. So that's all. Thanks for joining for the class and see you next Sunday. So thank you. Thank you for joining the session. Bye.